Human understanding of reality is intrinsically bound to the development of systems of knowledge that enable the abstraction, modeling, and prediction of natural phenomena. Among these systems, mathematics and physics stand as the most rigorously structured and universally applied. Their interrelation forms the intellectual backbone of modern science. Mathematics, originating from practical needs such as trade, astronomy, and construction, evolved into a formal language capable of expressing the laws that govern the physical world. Physics, in turn, emerged from the human drive to comprehend the underlying principles of nature, refining itself through empirical observation and theoretical formulation. Together, these disciplines articulate the mechanisms of reality with a precision unmatched by any other form of inquiry. The foundational premise of mathematics lies in its axiomatic structure, where a minimal set of assumptions gives rise to complex systems of relations through logical deduction. This capacity for internal consistency and generalization makes mathematics a unique tool for modeling reality. Numbers, functions, sets, spaces, and transformations are not mere abstractions. They are frameworks through which the regularities of the universe can be expressed and understood. The transition from arithmetic to algebra, from Euclidean geometry to differential geometry, from classical logic to set theory, reflects an ongoing process of refinement and expansion driven by both internal developments and external demands posed by the physical sciences. Physics, in its modern form, begins with the scientific revolution, marked by figures such as Galileo. It was Newton who, by unifying terrestrial and celestial mechanics through the laws of motion and universal gravitation, demonstrated the power of mathematical description in capturing the dynamics of nature. The Newtonian paradigm prevailed for centuries, not merely because of its explanatory scope but because of its predictive power. The use of calculus developed by Newton and Leibniz allowed for the formulation of differential equations describing motion, leading to a systematic understanding of mechanics, optics, and thermodynamics. However, the physical world did not remain within the bounds of Newtonian determinism. The development of electromagnetism in the 19th century, culminating in Maxwell's equations, revealed that electric and magnetic fields could propagate through space as waves, governed by a unified set of mathematical laws. This theoretical unification, while successful, planted the seeds for the eventual breakdown of classical physics. The emergence of quantum mechanics and relativity in the early 20th century exposed the limitations of classical assumptions. Phenomena at atomic and cosmological scales required new mathematical structures: Hilbert spaces, operator theory, tensor calculus that not only described observations but challenged the intuitive notions of space, time, and causality. Quantum mechanics, in particular, redefined the concept of reality. Its probabilistic nature, encoded in the wave function and governed by the Schrödinger equation, defied classical determinism. The observer became an integral part of the physical system, and measurement was no longer a passive act, but an interaction that altered the system itself. The mathematical formalism of quantum theory, despite its abstract nature, proved remarkably successful in predicting experimental outcomes. Quantum field theory, an extension of quantum mechanics incorporating special relativity, led to the Standard Model of particle physics, a comprehensive framework describing electromagnetic, weak, and strong interactions among fundamental particles. Each advancement in quantum theory corresponded to mathematical innovations, further entrenching the symbiotic relationship between the two disciplines. Relativity theory, both special and general, introduced by Albert Einstein, revolutionized our understanding of space, time, and gravity. Special relativity unified space and time into a four-dimensional continuum, where the speed of light remained invariant for all observers. General relativity, a geometrical theory of gravitation, replaced the Newtonian concept of force with a curvature of space-time described by the Einstein field equations. These equations, deeply rooted in differential geometry and tensor calculus, provided a new mathematical paradigm for understanding the cosmos. Black holes, gravitational waves, and the expansion of the universe. All predictions of general relativity have been confirmed by empirical observations, reinforcing the notion that mathematical structures can capture the essence of physical reality. The epistemological implications of these developments extend beyond technical achievements. They raise profound questions about the nature of mathematics itself. Is it discovered or invented? Does it exist independently of the human mind, or is it a construct shaped by cognitive and cultural factors? While the majority of scientists and philosophers tend to view mathematics as a human invention or symbolic system devised to organize sensory data and formalize patterns, there exists a minority that considers it a discovery akin to uncovering the intrinsic architecture of the universe. The uncanny applicability of mathematics to physical laws, the so-called unreasonable effectiveness of mathematics, continues to challenge simplistic interpretations of its role. Moreover, the question of whether mathematics is ontologically fundamental, whether the universe is, in essence, mathematical, remains an open philosophical problem. Platonists argue that mathematical entities have an objective existence in a realm of forms, while formalists and constructivists emphasize the procedural and human-centered nature of mathematical activity. Physics, in its empirical methodology, does not adjudicate this metaphysical debate, but it is undeniably constrained and guided by mathematical necessity. The physical world appears to obey mathematical principles, whether through conservation laws, symmetries, or probabilistic distributions, suggesting a deep structure that mathematics reveals rather than merely describes. The philosophical foundation of scientific inquiry, therefore, precedes and underpins both mathematics and physics. Every scientific theory, no matter how empirically successful, rests on a set of assumptions, epistemic, metaphysical, and methodological, that cannot be derived from the theory itself. The choice to assume that natural laws are uniform across time and space, for example, is not empirically verifiable, but is necessary for the coherence of scientific practice. Similarly, the reliance on logic and the law of non-contradiction is a philosophical commitment, grounds the possibility of proof and falsification. Thus, philosophy, rather than being a speculative supplement to science, is its indispensable framework. It is crucial to highlight that science, in its strict sense, deals only with what is observable, measurable, and falsifiable. Questions concerning meaning, purpose, or the existence of non-material entities fall outside its scope, not because they are illegitimate, but because they cannot be tested through empirical means. The boundary between science and metaphysics is not always clear-cut, especially in areas such as cosmology, where observational limitations force reliance on theoretical Nonetheless, maintaining methodological rigor ensures that scientific claims retain their predictive and explanatory power. This distinction has implications for the debate on the origin and nature of reality. While scientific theories can describe how the universe behaves and possibly how it began, they do not address why it exists or whether it has a purpose. These are philosophical or theological questions, not scientific ones. The Big Bang Theory, for example, explains the expansion of the universe from an initial singularity, supported by observational data such as cosmic microwave background radiation and the redshift of galaxies, but it does not explain why there is something rather than nothing, nor what preceded the singularity if such a notion even makes sense within current frameworks. As our understanding deepens, it becomes apparent that the universe is structured at multiple scales, each governed by different dominant forces and described by different effective theories. At the macroscopic level, classical mechanics and general relativity provide accurate models. At the atomic and subatomic levels, quantum mechanics reigns. At the interface, such as in black hole thermodynamics, or the early moments of the universe, our current theories break down, and a unified theory of quantum gravity is sought. String theory, loop quantum gravity, and other speculative frameworks aim to reconcile these domains, each proposing new mathematical architectures that could underlie all of physical reality. The pursuit of a theory of everything is not merely a technical endeavor, but a conceptual revolution that would redefine our understanding of existence. It challenges our current distinctions between space and time, matter and energy, information and substance. Concepts such as extra dimensions, holography, and entanglement suggest that reality is far more complex and perhaps more abstract than our everyday experience implies. If proven empirically, such theories would not only alter the landscape of physics, but also demand a re-evaluation of the metaphysical assumptions underlying our worldview. This ongoing dialogue between observation, theory, and philosophy underscores the dynamic nature of human knowledge. It is not a linear progression toward absolute truth, but a spiral of approximation, where each revolution brings greater clarity in deeper questions. The role of the observer, the limitations of language, the structure of logic, and the contingency of perception, all these factors influence what we consider to be real and knowable. The very act of knowing is embedded in a matrix of precepts, practices, and purposes that shape the content and form of what is known. If you're enjoying this exploration into the profound connections between physics, mathematics, and philosophy, consider subscribing to the channel and turning on notifications. It is the best way to stay connected with content that challenges your mind and expands your perspective. Your engagement helps bring these reflections to a broader audience. Let us keep this intellectual journey alive. Subscribe now and don't miss what's coming next. The educational and practical implications of understanding mathematics and physics extend into every facet of human life. From technology and medicine to economics and environmental science, the capacity to model and predict complex systems is vital. Yet this practical utility should not overshadow the deeper existential dimension. Studying the universe is also a way of studying ourselves, of confronting the limits of our perception and the scope of our imagination. The microcosm and the macrocosm reflect each other in structure and principle, not metaphorically, but through the isomorphisms that mathematics makes visible. The atom and the galaxy, though separated by orders of magnitude, are connected by the same fundamental laws, revealing an underlying unity that defies the fragmented nature of our everyday experiences. The nature of space and time, for instance, is not intuitively grasped. Our sensory experience gives us a sense of extension and duration, but physics reveals these as relative constructs, dependent on the frame of reference and the curvature induced by mass and energy. Time dilation and length contraction and special relativity are not mere thought experiments. They are measurable phenomena confirmed by satellite-based technologies. Similarly, the curvature of space-time around massive bodies, predicted by general relativity, has been observed through the bending of light and the detection of gravitational waves. These observations do not merely confirm equations. They redefine what we mean by space and time. Quantum mechanics further complicates our understanding. The principle of superposition, the uncertainty principle, and quantum entanglement suggest a world that is fundamentally indeterminate and objects do not have definite properties independent of measurement. Instead, properties emerge through interaction. This challenges classical notions of realism and locality, raising profound questions about causality and the role of the observer. Interpretations of quantum mechanics, such as the Copenhagen interpretation, many worlds theory, or objective collapse models, each carry philosophical implications, none of which can be resolved solely through experiment. The interplay between determinism and probability in quantum physics exemplifies a broader tension between predictability and uncertainty in human knowledge. While deterministic models offer control and precision, they often fail to capture the stochastic nature of real-world systems. Probability, far from being a concession to ignorance, becomes a fundamental component of the laws themselves. Statistical mechanics, quantum field theory, and even genetic inheritance rely on probabilistic frameworks. This probabilistic dimension of reality, as revealed through quantum mechanics and statistical models, alters our philosophical stance on determinism and free will. In a classical Newtonian framework, the universe was seen as a grand clockwork mechanism, predictable and governed by immutable laws. Such a universe leaves little room for genuine freedom or contingency. However, the quantum framework introduces inherent unpredictability at the most fundamental level, suggesting that not all events are causally determined. While this does not directly affirm the existence of free will, it does dismantle the assumption that every aspect of the universe, including human behavior, is fully predetermined by prior states. The philosophical consequences of this shift extend into ethics, psychology, and even legal theory, where notions of accountability and agency hinge on interpretations of determinism. Moreover, the convergence of quantum theory and information theory has opened a new frontier in understanding reality as fundamentally informational. The rise of digital physics, a speculative yet increasingly influential perspective, posits that the universe might be better understood as a computational structure. In this view, matter and energy are secondary to information, and the laws of physics are akin to software running on a cosmic hardware. This reconceptualization challenges traditional materialism and aligns, in part, with ancient philosophical traditions that viewed the world as an illusion or simulation. While such theories remain on the speculative edge, they reflect a growing recognition that the fabric of reality may be structured not by substance alone, but by relationships, data, and codes. These considerations lead to broader ontological questions. What does it mean for something to exist? Is existence an absolute category, or is it a function of relational properties within a system? Quantum field theory, for instance, describes particles not as isolated entities but as excitations in underlying fields. The concept of a particle emerges from the interaction of fields and measurement apparatus, blurring the distinction between object and environment. Similarly, the identity of a particle is not a static essence, but a set of quantum numbers and probabilistic behaviors. This challenges the classical notion of substance and invites a process-oriented ontology, where being is defined by interaction and change. Cosmology extends these ontological inquiries to the largest scales. The observable universe is not the entirety of existence, but a horizon determined by the speed of light in the age of cosmic expansion. Beyond this horizon may lie an unobservable multiverse, with different physical constants, dimensions, or even laws of logic. The hypothesis of a multiverse, while unprovable by current means, arises naturally from inflationary cosmology and string theory. If true, it would redefine the anthropic principle not as a statement about fine-tuning by design, but as a selection effect among countless possibilities. In such a framework, the emergence of life and consciousness may be statistically rare yet inevitable in an ensemble of universes. These cosmic scales confront us with the paradox of human significance. On one hand, we are infinitesimal in size and duration compared to the universe. On the other, we are the only known entities capable of contemplating the cosmos and formulating its laws. This duality, our smallness and our is a cold, hard problem of consciousness, how subjective experience arises from physical process, and some theorists suggest that consciousness may be a fundamental feature of the universe, not an emergent one. Pan's and quantum consciousness are attempts to address this enigma, though none have achieved consensus. In parallel, the philosophy of mathematics continues to evolve. New developments in logic, category, theory, and foundations have reframed our understanding of mathematical truth. Gödel's incompleteness theorems, for instance, demonstrated that no sufficiently powerful formal system can be both complete and consistent, implying limits to what can be known within any axiomatic framework. This result does not undermine mathematics but enriches its philosophical depth, suggesting that mathematical truth transcends formal probability. In a similar vein, the continuum hypothesis and other set theoretic questions highlight the independence of certain statements from foundational axioms, pointing to the plurality of possible mathematical universes. Mathematics, therefore, is not a monolithic edifice, but a dynamic and pluralistic domain. Different branches, algebra, topology, analogous, combinatorics, offer diverse perspectives on structure and relation. Their interplay produces rich landscapes of inquiry, often with unexpected applications in physics, computer science, and biology. The unity of mathematics lies not in a single foundation but in the coherence and fertility of its This internal coherence is mirrored in the way physical theories, despite their diversity, often converge on common mathematical structures. Symmetry groups, differential equations, and statistical models recur across domains, suggesting that mathematics is not only a language of science but a map of reality. In educational terms, the neglect of mathematical and physical literacy is a profound societal limitation. Individuals who lack basic numerical and scientific understanding are more vulnerable to financial manipulation, health, misinformation, and technological dependency. As the economy becomes increasingly data-driven, the demand for quantitative reasoning and algorithmic thinking grows. Mathematics is not merely a scholastic requirement. It is a cognitive framework for navigating complexity, assessing risk, and making informed decisions. Similarly, physics provides a foundational understanding of energy, matter, and motion concepts that underlie all technological systems. The decline of mathematical engagement is often attributed to poor pedagogical methods and a failure to connect abstract concepts to meaningful applications. However, the root problem is deeper: a cultural undervaluing of rigorous thought and delayed gratification. Mathematics requires sustained effort, patience, and logical discipline qualities, increasingly at odds with a culture of immediacy and distraction. Restoring the value of mathematical education entails not only curriculum reform but a broader shift in cultural attitudes toward knowledge, effort, and intellectual challenge. This challenge is also philosophical. The instrumental view of education as a means to employment obscures its deeper function. The formation of critical, autonomous minds, mathematics and physics, at their best, cultivate habits of thought that transcend vocational utility. They train individuals to distinguish evidence from opinion, to analyze arguments, and to question assumptions. In an age of misinformation and ideological polarization, these skills are not luxuries but necessities. The scientific method, with its emphasis on skepticism, revision, and empirical testing, offers a model of rational inquiry that is essential for democratic societies. If you've made it this far, It's clear you're deeply invested in understanding the universe and the structures that govern it. Take a moment to like and share this video. It helps signal to the platform that this kind of thoughtful content matters. Your engagement ensures that more people encounter ideas that truly expand perspective and challenge convention. Let's build a community grounded in knowledge. Like and share now. At the frontier of knowledge, science encounters its limits not as failures, but as invitations to deeper inquiry. The origin of time, the nature of dark matter and dark energy, the reconciliation of quantum mechanics with general relativity. These are not only technical puzzles but windows into the metaphysical structure of the universe. Each discovery opens new questions, reminding us that science is an open-ended pursuit, not a closed system of certainties. Its power lies not in providing final answers, but in revealing the profound intelligibility of the world and the inexhaustible depth of what remains unknown. The pursuit of understanding reality through science inevitably leads us into territories where the boundaries between physics, mathematics, and philosophy become At the heart of this convergence lies a fundamental recognition. Every model, every equation, every empirical law is not the thing itself, but a representation, a map, not the territory. Yet the precision and universality with which these maps predict and explain phenomena suggest that they are not arbitrary conventions but reflections of an underlying order. This raises the persistent metaphysical question: is the universe inherently intelligible, or do we impose structure upon it to make it comprehensible? One of the most compelling arguments for the inherent intelligibility of the universe is the success of symmetry principles in physics. From Noether's theorem, which links symmetries to conservation laws, to the classification of elementary particles via group theory, symmetry serves as a unifying motif. However, not all aspects of the universe conform to this elegant symmetry. Spontaneous symmetry breaking, for instance, explains how uniform laws can give rise to complex and differentiated phenomena. The Higgs mechanism, by which particles acquire mass, involves the breaking of electroweak symmetry. In a similar vein, cosmological inflation proposes a mechanism by which the early universe transitioned from a highly symmetrical state to one of increasing structural complexity. Thus, asymmetry becomes as essential as symmetry in explaining the world, highlighting that mathematical beauty, while often a guide, is not an absolute criterion for truth. The tension between elegance and accuracy is further exemplified in the search for a unified theory. String theory, with its elegant mathematical formulations and higher dimensional spaces, aspires to reconcile general relativity and quantum mechanics. Yet, despite its internal consistency and theoretical appeal, it has yet to produce testable predictions. Critics argue that this renders it more mathematical metaphysics than empirical science. Others contend that the lack of empirical confirmation is a temporary state due to current technological limitations. The debate reflects deeper epistemological issues. Should a theory be judged primarily by its empirical or can mathematical coherence and unification suffice as provisional justification? This question resonates beyond string theory. In cosmology, models of the early universe and dark energy often involve parameters and entities that are difficult or impossible to test directly. The fine-tuning of physical constants, for instance, suggests that even minor variations could render the universe inhospitable to life. Some interpret this as evidence of design, while others invoke the anthropic principle. We observe a life-permitting universe because only such a universe can be observed. The multiverse hypothesis offers a naturalistic framework for this principle, but at the cost of empirical accessibility. These debates highlight the philosophical dimension of science. The criteria by which theories are accepted are not purely empirical, but involve judgments about simplicity, explanatory scope, and ontological parsimony. Another philosophical tension arises in the interpretation of physical theories. Quantum mechanics, in particular, admits multiple interpretations, each with different implications for reality. The Copenhagen interpretation emphasizes the role of measurement and the observer, collapsing the wave function into a definite state. The many worlds interpretation posits that all possible outcomes of quantum measurements are realized in branching universes. Objective collapse theories introduce mechanisms by which wave functions collapse without observation. Each interpretation reproduces the same empirical predictions, but offers a radically different picture of the world. This underdetermination raises questions about the nature of scientific truth and the relationship between theory and ontology. These issues are not confined to theoretical physics. In applied domains, such as climate science, epidemiology, and economics, models serve as tools for prediction and policy, yet they are inevitably simple. The selection of variables, assumptions about causality, and methods of calibration all involve judgment. The trustworthiness of a model is not only a matter of its past performance, but also of its transparency and interpretability. The replication crisis in psychology and other social sciences further underscores the importance of methodological rigor and statistical literacy. Misuse of mathematical models, whether through ignorance or manipulation, can lead to real-world harm, eroding public trust in science. To address these challenges, scientific education must emphasize not only technical competence, but philosophical clarity. Understanding the limits of models, the assumptions behind equations, and the criteria of theoretical justification are as important as computational skills. Philosophy of science should not be an afterthought but an integral part of scientific training. It equips practitioners with the tools to critically evaluate their methods, to distinguish between robust knowledge and speculative hypotheses, and to communicate uncertainties responsibly. Equally important is the cultivation of public scientific literacy. In an era where misinformation spreads rapidly, the ability to evaluate claims, interpret data, and understand probabilistic reasoning is essential for informed citizenship. This is not merely a technical issue but a democratic one. Decisions about public health, environmental policy, and technological regulation depend on collective understanding and rational debate. The failure to communicate science effectively, or to recognize the epistemic boundaries of science, can have catastrophic consequences. Within this broader context, the role of the scientist takes on ethical dimensions. The pursuit of knowledge is not value neutral. It is embedded in social, political, and economic systems. Scientists must navigate the tension between curiosity-driven inquiry and the demands of funding, publication, and institutional prestige. They must also contend with the potential uses and misuses of their work. The development of nuclear weapons, surveillance technologies, and artificial intelligence illustrates how scientific progress can outpace ethical deliberation. A responsible science is one that anticipates consequences, engages with the public, and participates in shaping the moral discourse around technology. Take a moment now to leave a comment below. What is your take on the philosophical role of science in society? Do you believe mathematical coherence is enough, or should we demand empirical proof above all? Your comment can spark a conversation that brings this community of curious minds even closer. Don't hold back, write your thoughts below and join the dialogue. This ethical awareness does not require scientists to become moral philosophers, but it does require a sense of responsibility for the broader implications of their work. Scientific integrity includes not only honesty in reporting results, but also humility in recognizing uncertainty and openness to alternative perspectives. In a pluralistic society, science must coexist with diverse worldviews and values. It must justify its methods and findings not only to peers, but to a public whose lives are affected by scientific decisions. This requires not only technical precision but rhetorical clarity, cultural sensitivity, and philosophical depth. In this light, science becomes not just a method of inquiry, but a mode of being, a commitment to reason, evidence, and continuous revision. It reflects a deeper human impulse to understand, to explain, and to find coherence in the vastness of experience. This impulse is not limited to scientists. It is shared by artists, philosophers, and all who seek to make sense of the world. The convergence of physics, mathematics, and philosophy is not an academic exercise but a testament to the unity of human reason. It reveals that the search for knowledge, while fragmentary and fallible, is also cumulative and convergent, a shared journey toward understanding. The human journey toward understanding reality is marked by an expanding frontier of knowledge, each new insight revealing further complexities and deeper. And as science advances, it does not simplify the universe but unveils its stratified intricacy, layers within layers of structure, scale, and causality. From the subatomic particles described by the Standard Model to the cosmic web of galaxies shaped by dark matter and dark energy, the narrative of science is not one of closure, but of ever-widening perspective. The apparent paradox is that the more we understand, the more we recognize the magnitude of what remains to be understood. This recognition does not signal failure but reflects the openness and vitality of scientific inquiry. One striking example of this dynamic is the ongoing search for a theory of quantum gravity. Both general relativity and quantum mechanics are immensely successful within their domain as cosmic and microscopic, respectively, but they are mathematically incompatible at extreme scales, such as those found in black holes and the early universe. The singularities predicted by classical general relativity, where density becomes infinite and space-time curvature diverges, signal a breakdown of the theory's applicability. Meanwhile, quantum mechanics lacks a coherent description of gravity, treating it as a classical background rather than a quantized field. This conceptual and mathematical disjunction has spurred the development of numerous candidate theories, from string theory and loop quantum gravity to causal dynamical triangulations and emergent spacetime models. What unites these diverse approaches is the recognition that spacetime itself may not be fundamental, but emergent. Just as temperature and pressure emerge from the collective behavior of molecules, space and time may emerge from deeper non-spatial, non-temporal degrees of freedom. The idea that geometry is not a background but a consequence of quantum entanglement and information flows has gained traction in theoretical physics. This represents a radical departure from the classical view of the universe as a stage on which events occur. Instead, space and time become dynamic players in the unfolding of reality, shaped by quantum interactions and informational networks. Such ideas are not merely speculative. They are driven by the need to resolve paradoxes and preserve the coherence of physical laws. The black hole information paradox, for instance, challenges our understanding of entropy, causality, and unitarity in quantum theory. If information is truly lost in black holes, then quantum mechanics would need revision. If not, then new mechanisms must explain how information is preserved. Recent developments such as the holographic principle and the firewall hypothesis attempt to reconcile these tensions, often relying on sophisticated mathematical tools and conjectures. These debates illustrate the philosophical depth of modern physics, where the line between empirical science and conceptual analysis becomes increasingly blurred. In this context, the epistemological role of mathematics becomes even more pronounced. Mathematics is not merely a language in which physics is expressed. It is a generative framework that shapes the very formulation of physical theories. The choice of mathematical structures, whether manifolds, Hilbert spaces, spin networks, or category-theoretic objects, profoundly influences the types of questions that can be asked and the kinds of answers that can be meaningfully proposed. This influence is not neutral or arbitrary. It reflects a deep interaction between the cognitive architecture of the human mind, the empirical constraints of observation, and the abstract structures of logic and number. The question of whether the universe is mathematical or merely behaves in ways that can be described mathematically remains unresolved. However, the extraordinary success of mathematical modeling across all scales and domains strongly suggests that the universe is not indifferent to structure. The recurrence of specific patterns, fractals in nature, power laws in distribution, symmetry in particles, and invariance in transformations points to an underlying regularity that mathematics captures with elegance and rigor. These patterns are not artifacts of measurement. They are the very substrate of what we observe. This realization has prompted some thinkers to propose that mathematics is not only descriptive but prescriptive, that the universe conforms to mathematical logic not by coincidence, but by necessity. Max Tegmark, for instance, argues in favor of the mathematical universe hypothesis, which posits that physical reality is a mathematical structure. While this view remains controversial and difficult to test, it raises profound questions about ontology and existence. If the universe is a mathematical object, then its properties, including those that give rise to life and consciousness, may be derivable from first principles. This would imply that existence itself is a theorem waiting to be proved, a notion that transforms metaphysics into a branch of mathematics. Yet, even if such a vision were confirmed, it would not eliminate the need for human interpretation, experience, and meaning. Science, no matter how complete, does not answer the existential questions of why there is something rather than nothing, or what it means to be conscious, moral, or free. These questions reside in the domain of philosophy, literature, and the arts. They are not inferior to scientific questions but complementary. The full picture of reality includes not only particles and fields but intentions, values, and experiences. These dimensions of existence are not reducible to equations, even if they are constrained by them. They reflect the richness of being that transcends quantification. In this broader vision, the integration of disciplines becomes essential. The separation between science and the humanities, often institutional and cultural rather than epistemic, is increasingly untenable. The complexity of modern problems, climate change, artificial intelligence, but historical perspective and philosophical clarity. The scientist therefore must also be a humanist, aware of the implications of knowledge and the context in which it operates. This integration does not dilute the rigor of science. It enhances its relevance and responsibility. Furthermore, The trajectory of scientific progress is not immune to socio-political influences. Funding priorities, institutional paradigms, and cultural narratives shape the direction of research. The dominance of certain models or approaches may reflect not only empirical adequacy, but also historical contingencies and power structures. Recognizing this does not invalidate science, but calls for critical reflection on its practices. The ideal of objective, self-correcting science must be upheld not through NA but through vigilant transparency, methodological pluralism, and intellectual humility. At its best, science is a collective endeavor that transcends individual ego, national boundaries, and ideological divisions. It is a testament to the human capacity for collaboration, curiosity, and wonder. It builds cathedrals of thought that stand for generations, open to all who seek understanding. The unity of mathematics and physics, grounded in the philosophical commitment to reason and truth, is one of humanity's greatest achievements. It affirms that, despite our limitations, we can grasp the deep structures of the universe, predict its behavior, and harness its forces for good or ill. This realization carries a moral imperative. Knowledge confers power, and power entails responsibility. As we probe deeper into the foundations of reality, we must also cultivate the wisdom to use that knowledge ethically. This includes respecting the autonomy of nature, preserving the conditions for life, and promoting justice in the distribution of technological benefits. Science must not only seek truth but serve the common good. Its pursuit must be guided not only by what can be done but by what should be done. In closing, the exploration of reality through mathematics and physics is not a purely academic pursuit. It is a human one. It connects us to the cosmos and to each other, grounding our understanding in shared principles and aspirations. It challenges us to think clearly, to question deeply, and to act responsibly. It reveals a universe that is not only comprehensible but profoundly ordered, inviting us to participate in its unfolding with humility and courage. Let's keep this intellectual momentum going. If you haven't already, hit the like button and share this video with someone who's passionate about science and philosophy. Your support helps ensure that deep, thoughtful content continues to thrive, and it takes just a click to make a big difference. Let's bring more minds into this conversation. Like and share now. This culmination of inquiry into the foundations of reality marks a pivotal moment in our intellectual development, not as the endpoint of understanding but as a recognition of the perpetual nature of questioning itself. The trajectory of science and mathematics, so often characterized by problem solving and modeled at a deeper level, the recursive structure of knowledge. Every explanation generates further inquiries. Every unifying theory exposes deeper contradictions or finer complexities. The recursive nature of knowledge mirrors the recursive nature of the cosmos, self-similar at different scales, unpredictable in detail, yet ordered in its fundamental symmetries. The implications of this realization are both epistemological and existential. Epistemologically, it challenges the notion of finality in science. The dream of a theory of everything may never materialize as a single all-encompassing equation, not because the universe is fundamentally chaotic or unknowable, but because any such theory would still be embedded within a framework of assumptions, interpretations, and representational limits. Mathematics itself is subject to this limitation. Gödel's incompleteness theorems remind us that in any sufficiently powerful formal system, there exist true statements that cannot be proven within that system. This incompleteness is not a flaw, but a feature. It signals the openness of mathematical inquiry and, by extension, of all human understanding. Existentially, this openness entails that meaning is not given by nature but created through our engagement with it. Science provides the structure within which such meaning can be constructed, but not the meaning itself. The laws of physics do not tell us how to live, what to value, or whom to love, yet they inform the conditions under which such questions can be meaningfully asked. They delineate the boundaries of possibility, and within those boundaries, human freedom finds its stage. The interplay between necessity and freedom, between law and creativity, is not a contradiction but a condition of human flourishing. This dialectic is evident in the very tools we use to understand the world. Mathematics, while abstract and precise, is also remarkably flexible and adaptive. It evolves in response to new problems, new technologies, and new conceptual frameworks. Non-Euclidean geometries, once seen as mere curiosities, became essential to general relativity. Complex numbers, initially met with skepticism, now underpin quantum mechanics and electrical engineering. Category theory, once confined to pure mathematics, now informs computer science and cognitive science. These shifts reveal that the boundaries between pure and applied, between theoretical and practical, are porous and contingent. Knowledge, like nature, is dynamic. Physics, likewise, has transformed not only our understanding of the universe but our place within it. From the heliocentric revolution that displaced the Earth from the center of the cosmos to the realization that humans are composed of stardust forged in ancient supernova, physics has repeatedly dissented the human perspective, yet paradoxically it has also ennobled it. To comprehend the cosmos, even partially, is a uniquely human capacity. The ability to construct abstract models, to verify them through experiment, and to refine them through critical debate is not a biological necessity, it is a cultural achievement. It speaks to the creative and cooperative nature of our species. In this context, science must be understood not as a static repository of facts, but as a living, collective endeavor. It is shaped by institutions, traditions, and practices that both enable and constrain its progress. Peer review, replication, and transparency are not bureaucratic formalities but epistemic virtues that ensure reliability and trust. They represent an ethics of inquiry, grounded in humility, rigor, and accountability. When these virtues are compromised, whether by ideological bias, commercial pressure, or political interference, the credibility of science suffers. Reaffirming these principles is essential not only for scientific progress, but for the maintenance of an informed and rational public sphere. Moreover, the integration of science with technology has created new opportunities and new risks. Artificial intelligence, genetic engineering, and quantum computing promise to transform society in ways we are only beginning to understand. These technologies, rooted in deep theoretical insights, raise questions about identity, autonomy, privacy, and equity. Who controls these tools? Who benefits from their applications? What values guide their development? These are not technical questions but moral and political ones. They require not only scientific expertise but democratic deliberation and philosophical reflection. This convergence of science and society calls for a new kind of literacy, one that combines quantitative reasoning with ethical discernment, technical knowledge with historical awareness. Such literacy cannot be outsourced to specialists. It must be cultivated broadly through education systems that value critical thinking, creativity, and interdisciplinary engagement. A scientifically literate society is not one in which everyone is a physicist or mathematician, but one in which people understand how scientific knowledge is produced, what it can and cannot tell us, and how it interacts with other domains of human concern. In light of this, the role of educators, communicators, and cultural institutions becomes central. They are the bridge between the technical languages of science and the everyday languages of meaning. Their task is not merely to simplify or popularize, but to contextualize and deepen. They must show that science is not a collection of dry facts, but a vibrant way of engaging with the world, a way that is rigorous yet imaginative, precise yet open. They must help cultivate the intellectual virtues that make science possible: curiosity, skepticism, patience, and a willingness to revise one's beliefs in light of new evidence. Perhaps most importantly, they must convey that science, mathematics, and philosophy are not separate silos but overlapping modes of inquiry. Together they offer a multi-dimensional perspective on reality, one that encompasses both explanation and interpretation, both mechanism and meaning. They invite us to see the universe not only as a system of interacting forces, but as a coherent whole, intelligible yet mysterious, governed by laws yet open to novelty. This holistic vision does not reduce complexity but embraces it. It recognizes that truth is not monolithic but layered, that understanding is not a destination but a process. In embracing this process, we affirm the value of reason in an age of uncertainty. We acknowledge that knowledge is provisional, that theories are models, and that certainty is rare. Yet we also affirm that truth matters, that coherence, evidence, and logic provide the best tools we have for navigating the world. In doing so, we reject relativism and dogmatism alike. We choose, instead, the path of critical engagement, a path that is demanding, but also deeply rewarding. And so, the exploration continues, from the subatomic to the cosmic, from the axioms of logic to the frontiers of consciousness, We are participants in a grand narrative of discovery. We may never reach a final theory, a complete system, or a perfect understanding, but in the striving itself, in the questions we ask, the models we build, and the communities we form, we enact the very essence of what it means to be human. Thank you for engaging with this long-form reflection. If this journey into the philosophical depths of science and mathematics sparks something in you, make sure to subscribe to the channel and tap the notification bell. New content like this is on the way, and your subscription ensures you won't miss it. Let's keep exploring together.